Okay, so for this next chapter, we're talking about oscillations, and I think oscillations are super cool because they can be very powerful, and there's something that are kind of hidden beneath the surface. We don't really notice them as much as we don't really notice them very much, but they're fundamental to the way mass interacts with other masses, and they're really important to every factor of our lives without us even realizing it. And so oscillations, we're just going to kind of start with the basics, like how to talk about them, why they exist, what causes them, or not even that stuff yet, just how we can describe the motion of something that's oscillating. So the first thing we're going to look at is I have an actual animation I found that I think is helpful, and this shows an oscillating system that consists of this mass hooked to this spring. Okay, and I want you to look at the graph created if we were to graph its position with respect to time. Okay, what does this look like to you? Hopefully you've noticed that this looks like some sort of trig function. Okay, and this is a very important and significant thing when we talk about oscillations. Okay, that their motion can be modeled with trig functions. So before we get into modeling it, we're just going to talk about a little bit of vocabulary. So we know this word, the period. So T stands for period, and it represents the amount of time it takes for one cycle, or let's say one complete oscillation to happen. Okay, so we'll talk about what that means in a second. Okay, so that's the time for one oscillation. Then we have this other word, frequency, which is the inverse of the period, which means the number of oscillations in 1 second. Okay, and we can find these because T is equal to 1 over F, and F is equal to 1 over T, which also means that T times F is equal to 1. Okay, and so this is kind of that relationship here between frequency and period. And just a little hint for you on your calculator, there's a button that probably looks like 1 over X or something like this. This is a really useful tool when you're switching back and forth because it will find the inverse of something for you. So anyway, that's time, oscillations. And we have this other term called angular frequency, which is analogous to angular speed. Okay, and this is the number of radians per second. Okay, and this is found by taking 2 pi, so number of radians in a full oscillation, dividing by the time, or multiplying 2 pi times the frequency. Okay, and so this angular frequency is basically, we represent it as the amount of time, or the speed at which something returns to its original position. So it's a rate that has to do with returning to your initial kind of starting conditions. Okay, and this is important, like the starting conditions, because if you look back at this animation, you see that it goes up. So like, let's say that this was our starting point right here. Okay, so it gets to here, it returns that starting point right here, but it hasn't completed a full cycle right there because it doesn't have its same direction of velocity, which is significant for it to be returning to its starting position. I don't know if that made sense or not, but that's an important piece here, that it returns to the same position along its cycle, okay, or its oscillation. Okay, so from here, let's go ahead and make a general formula. So if this represents the motion of an object, okay, let's say it's an oscillating spring. If we were to release it from this point and let it start oscillating like up and down like this, initially it would have no motion here, and that's why we kind of start with a velocity here of 0. As it goes down, that velocity increases and then slows as it gets to the bottom, and then it turns back around slows down as it gets to the top, and repeats that cycle over and over. Okay, well, if we want to create a model for this, this is a cosine function, and so we're going to use cosine. Okay, now no matter what number you put into here, the greatest number that you can get out of cosine is equal to 1. Okay, so the way that we account for the magnitude of these oscillations, let's say that this had a height, let's say it had some like resting equilibrium position here that we'll call like position 0. And let's say we lifted it up to a height maybe of 20 centimeters, or about 0.2 meters. Well, the way we would account for this, we know that it's only at that position here and here, well, we multiply it in the beginning. So 0.2 times cosine, and so it gets to 0.2 here and here, which means that at this point, when cosine gives a value of -1, we have a position of -0.2. So this piece right there represents our amplitude. Okay. So next piece will go inside of here, and it'll be kind of control the rate at which this, or kind of represent or match up the rate at which it kind of completes a cycle. Okay, and so when something's oscillating, it's changing its position with respect to time. So I want to put a piece here for time. But the problem is, if we just put time here, it's not going to give us what we want, because cosine as a function only returns to this starting point every complete cycle, which is 2 pi radians, 1 full rotation. Okay, and so in order to take this and make this match up with this, we have to use angular frequency. And what it does is it takes this value for one cycle, 2 pi, and divide it by the time for one cycle, or the period, and then we'll multiply that here by the time. So like, for example, if we have 1/2 cycle, which would be like t/2, then when we multiply omega t right here, that'd be 2 pi over t times t/2, and that would just give us pi, or 1/2 cycle. Okay, and so that's why we have this omega t right here. And then there's one other piece, and so because this is cyclical, you can really start watching at any point. So maybe you start watching it right here, or maybe you start watching it here at the bottom, or right here. You can really start tracking it whenever. And so we add this little piece here called phi that represents our phase shift, okay, or how far the graph is shifted from its normal starting point. And that's how we account for it there. We're going to mostly not use that in here, because it gets things get a little tricky with that. So this is going to be kind of our standard equation though. Just as a refresher, A stands for amplitude. Okay. This is angular frequency. And this is phase shift. Okay. Okay, so let's try this out. So we have this will be a spring mass system that's oscillating. It was at its equilibrium position, and it was raised up a height of 30 centimeters or 0.3 meters and allowed to oscillate. And let's say that when it starts to oscillate, it completes 10 cycles in 3 seconds. All right, and so our goal here would be to maybe sketch a graph of its position, as well as to make an equation for its position. Okay, so if we say we're going to start at the beginning where we released it, it's going to start here, it's going to go down, come back up, in the world's ugliest cosine graph. Okay, something like that. And then we could put some values here. So like, what was the time for one complete cycle? Well, if it had 10 cycles in 3 seconds, then the period would be what? Be 0.3 seconds. Okay, which means that for 1/2 cycle here, that would be 0.15 seconds. What would be our amplitude? would be the height that it's been lifted, or 0.3 meters. So that's negative 0.3 and positive 0.3. Okay, so now let's write our equation. So a cos omega t plus phi. Okay, since it's starting from this initial cosine starting point, phi is going to be equal to 0. Okay, so let's put in our other pieces, our amplitude. And so amplitude is really how we kind of take this and connect it to reality as far as like how big something's oscillation is. And so in this case, it's going to be 0.3 meters. That'd be the maximum distance away. Cos, and then we need to figure out what omega is. Okay, so remember, omega is the time it takes to complete 2 pi radians. So that'd be 2 pi radians is a complete cycle. So that would be over 0.3. So 2 pi over 0.3. So we put that in right here. And now we have a function for the position of this spring with respect to time.